Welcome students. Today I am going to discuss you application of Biot law. In your syllabus there are two applications. That is, one is magnetic field intensity due to current carrying circular coil. Another is magnetic field intensity due to circular loop. Let's see. First I am going to discuss with you, that is magnetic field intensity due to circular current carrying circular coil. Let's take a circular coil. Here I am making a figure, a circular loop coil, in which current is flowing, suppose I, and we want to calculate magnetic field intensity at center of coil, that it is O. Current is passing in the coil is I. We take a small part of the coil, that is dl, and we just, let's suppose the distance from dl to center, that is radius of coil, and that is taken r. Now my dear students, you see here we apply here the magnetic field intensity due to this current element. We see the direction of magnetic field is always perpendicular to the dl as well as r, because I am getting ideal. You know the formula of magnetic field intensity, dV is equal to mu 0 over 4 pi I dl cross r. Hence the magnetic field intensity is perpendicular to both current element as well as the radius vector. This is the cross product, so we are getting the magnetic field intensity on center, that will be the perpendicular to downward. This is cross here. Now with all element, if I am considering on the coil so many, the direction of magnetic field intensity is always perpendicular to the coil, and it is inside the coil. Let's see. Let a coil having current I of radius r. We consider I am going to discuss this one. We consider magnetic field intensity due to current element I dl. Here we know that magnetic field formula is dV is equal to mu 0 over 4 pi I dl sin theta over r square. We write here the formula. We find here, if I am using removing the vector notation, that will be I dl r sin theta over r square r cube into unit vector r here. This will be cancelled out, and here you having r square. Now you see, if we apply here the magnetic field formula, here sin theta is 90 degree, so sin theta becomes 1. So we have dV is equal to mu 0 over 4 pi I dl over r square. Magnetic field due to the whole coil, if we are considering, and that will be the length of coil becomes 2 pi r, that is the length of coil. Means our magnetic field will be start from 0 to 2 pi r. So the total magnetic field will be 0 to 2 pi r dB. We use here 0 to 2 pi r mu 0 over 4 pi I over r square into dl, and we take here the outside mu 0 over 4 pi I over r square, and this will be here 0 to 2 pi r. Magnetic field we are getting B is equal to mu 0 over 4 pi I over r square into 2 pi r. So we are having here B is equal to mu 0 over 2 I over r. This is the magnetic field intensity due to a coil at the center of coil. If coil has n turn, then magnetic field formula becomes B is equal to mu 0 over 2 Ni over r, because the length becomes 0 to 2 pi nr. So we use here the n is the number of turn of the coil, and we can calculate here. This is the one application, and we get it here. Now the second application, magnetic field intensity due to circular loop. Due to circular loop, let's see. We consider a loop. It is a circular loop, and we take a center of the loop and we draw a line let loop have the radius a, and we take a x distance p where we consider the magnetic field intensity, and we consider the dl here a small element, and due to this we are calculating, let p the point here. Unfortunate, that is some mistake. We take here the angle phi, then the direction of magnetic field will be dB, and we get, if we resolve it, we get two component. Here it is phi, this will also phi, and that is perpendicular. Now this will be d cos phi, and this will be dB sin phi. Here are so many assumptions, let's see. Let a loop of radius a, we take a point lies on the axis of loop where we calculate magnetic field. Dear students, we take here assumptions. One assumption here, the angle made by current element is about, that is 90. Then if we apply here the formula dB equal to mu 0 over 4 pi ideal sin theta over r square. This will taken as a r. So from this we have the value of theta. Let a loop of radius a. We take a point lies on the axis. Point P we can take lies on the axis of the loop where we calculate magnetic field. We see that angle on P by current element is phi. And we get a dB magnetic field. If we consider the whole coil, whole loop as a current element, by considering whole loop element, we see that only dB sin phi will provide resultant magnetic field. How? Let's see. If we consider here, and we take a different color also. So you see, if we are taking here if this angle is also phi supposed to be, the magnetic field will be here the dB, and one component we get here, that will be dB cos phi, and since this will also phi, and here dB sin phi. Let's see, dB cos phi will cancel out by, if we consider 3-dimensional figure, you will find all component having, and then dB cos phi will cancel out, only the resultant you will obtain due to the dB sin phi. So we use this and we calculate, applying formula dB is equal to mu 0 over 4 pi ideal sin theta over r square. One consideration is here, if OP is very large, means A is very less than X, then theta is almost 90. So our sin theta becomes then our sin theta, sin 90 becomes 1, and here we use this. So our formula becomes dB is equal to mu 0 over 4 pi r dl over r square. Here the value of r under root a square plus x square. Okay, if coil has n turn, another thing we can calculate the resultant magnetic field will be B is equal to 0 to 2 pi a dB sin phi. Now what will be the sin phi value? That will be a upon under root a square plus x square. You can see from the figure. Now we use here putting all this value. We can take another assumptions also. If loop has n turn, then dB 0 to 2 pi n a dB sin phi. We put this value 0 to 2 pi n a mu 0 over 4 pi I dl over r square, that is a square plus x square, and here the sin phi value. Sin phi value we can write 0 to 2 pi n a mu 0 over 4 pi I dl over a square plus x square into a over under root a square plus x square. We take outside the constant term which are not integrated. 4 pi I a over a square plus x square, and that will be 3 by 2, and here 0 to 2 pi n a into dl. The value becomes mu 0 over 4 pi I a over a square plus x square 3 by 2, and this will be 2 pi n a. How? Let's see. Mu 0 over 4 pi I a square plus x square 3 by 2 L 0 to 2 pi n a. We cancel here. Here we are having 2, and our formula becomes mu 0 over 2 n I a square plus x square 3 by 2, and this is the magnetic field value. If we take one case 1, if x is let 0, means case 1, then what will happen? We put the value and we get the mu 0 over 2 n I a square, here a square into 3 by 2, this will be cancelled out, and you are having mu 0 over 2 n I over a. This is the formula of coil. We have calculated already. The same thing here we are getting. Means if you want to calculate on center, you will get this. If you want to calculate on the axis, you will get that formula. And by this you can use by using the Biot-Savart rule, we can calculate this also. Another use which is not in your syllabus, we will calculate in further different way. A long wire if you are considering, and we want to calculate the magnetic field at here, and if this distance is this way, we are taking, if this is angle phi 1, and this is phi 2. Then magnetic field will be mu 0 over 4 pi I over A. This distance is A, suppose. Then sine phi 1 plus sine phi 2. This is a formula for you for the calculation of this long wire if you want to calculate the magnetic field. For long wire in finite length, then that will be mu 0 over 2 pi I upon A. For infinite length, means current carrying wire having infinite length is straight wire. Infinite length, B is equal to mu 0 over 2 pi I over A. How it will be obtained? We will use in different way by solving another rule, that is I will give you it in my next video. Please keep in touch. Please like and subscribe my channel SM Physics Academy, and write comment in comment box. If any doubt you have, you can ask, and please click the bell icon for further notification. Thank you very much.